Have you ever really stopped and thought about where our digital world actually lives? Every photo you take, every video you watch, every document you save, it all has a physical home somewhere. In this explainer, we're going to take a pretty incredible journey into that physical world, from the spinning platters that basically defined an era to, get this, the very building blocks of life itself. So to set the stage, by 2025, it's estimated that humanity will be generating about 175 zettabytes. What's a zettabyte? Well, it's a 175 with 21 zeros after it. Yeah, it's an amount of information it's almost impossible to wrap your head around. So that brings up the really big question, right? Where are we going to put all of this stuff? And this isn't just some fun thought experiment. It is one of the single biggest engineering challenges of our time. To even begin to find an answer, we first need a map. We have to understand the vast universe of data storage as it exists today, from the impossibly fast to the unbelievably dense. You see, inside every computer, there is this massive gap, a performance cliff, really, between its super fast short-term memory and its much slower long-term storage. And bridging that divide, well, that's the name of the game. Okay, check this out. This is the storage hierarchy, and the best way to think of it is like a pyramid. At the very, very top, you have insanely fast and crazy expensive CPU registers. As you move down the pyramid, storage gets way cheaper and a lot denser, but it also gets much, much slower. Now, the key thing to see here is the huge jump between RAM and even a fast SSD. We're talking about an access time that increases by over 1,000 times. That is the performance cliff we have to cross every single time you open a file. So let's start at the bottom of that pyramid with the old workhorse that's been storing our data for over 60 years, the hard disk drive. Now, for all its slowness by today's standards, it is a true mechanical marvel. The core conflict in the storage world, the big battle, really comes down to this one question. Are there physical moving parts inside, or is everything solid state with no movement at all? This is the fundamental difference we're about to dive into. So an HDD is basically a microscopic record player. You've got this physical arm with a read-write head that literally flies nanometers above a spinning magnetic platter. And the first one, back in 1956, it held just 5 megabytes of data and was the size of 2 refrigerators. No joke. Today, we can cram multiple terabytes into something that fits in the palm of your hand. The crucial point here is that because it's a physical device, it's slow. Every time your computer needs a file from an HDD, it has to deal with 3 different delays. First, the arm has to physically move to find the right track. That's the seek time. Then, it has to wait for the platter to spin around to just the right spot. That's rotational latency. And only then can it actually start to transfer the data. This whole process is what you used to hear as that clicking or thinking sound in old computers. But then, a revolution happened, the Challenger technology that just changed everything by getting rid of all those moving parts. Enter the solid-state drive. Okay, so forget the record player. Think of an SSD as a massive grid of microscopic rechargeable batteries called flash memory cells. To store a 1, it basically traps electrons in a cell. To store a 0, it just lets them go. And because there are 0 moving parts, access isn't mechanical, it's all electronic, and it happens at a blistering, silent speed. But here's the thing, not all SSDs are created equal. The real innovation over the years has been figuring out how to store more and more bits of data in each of those tiny cells. With single-level cells, or SLC, you get 1 bit. It's incredibly fast and durable, but also really expensive. As you move down to TLC or QLC, you're packing 3 or even 4 bits into that same cell. This makes the drives much, much cheaper and larger, but it does come at a cost. Both the speed and the long-term endurance go down. It's a constant engineering trade-off. So, we've got these incredibly fast drives now, but a fast drive is totally useless if the road connecting it to the rest of the computer is just a slow, bumpy country lane. For years, that road was called SATA. It was a data highway, sure, but it was designed for the leisurely pace of those old spinning hard drives. For a modern SSD, its maximum speed of around 600 megabytes per second became a massive, massive bottleneck. So the solution was to build a brand new road, actually more like a superhighway. It's called NVMe. Instead of that old SATA interface, NVMe uses a direct multi-lane connection called PCIe to talk right to the computer's processor. It's a system designed from the ground up for one thing and one thing only: the insane speed of flash memory. And the difference in speed is, well, it's staggering. A SATA SSD pretty much tops out around 600 megabytes per second. A Gen 3 NVMe drive just blows past that at over 3,000. And with the latest Gen 5 drives, we're seeing speeds of 14,000 megabytes per second, or even more. This incredible performance leap is one of the biggest reasons that modern computers feel so snappy and instantly responsive. So, we've gone from refrigerator-sized machines to silent little chips that are thousands of times faster. It's been an amazing ride. But what's next? Well, let's look at the truly mind-bending future of storage. You know, the ultimate challenge in storage, the holy grail, is density. How much information can you possibly pack into the smallest possible space? It turns out, nature already solved this problem billions of years ago.
What if I told you that we could store everything? Every movie, every website, every song, every document ever created in a space that weighs just about this much, 1 kilogram.
Using DNA, that's right, by translating the zeros and ones of digital data into the 4 base pairs of DNA, A, C, G, and T, we could achieve a storage density so immense that a single kilogram could hold all the data on Earth. And it would be stable for thousands of years. It would be a perfect archive for our entire civilization. Now, this is still incredibly slow and unbelievably expensive today, but it raises a fascinating question for the future. As our data universe continues its exponential expansion, is our future going to be written on silicon chips that last for decades, or will it be woven into the biological strands that could last for millennia?